So the difference between what we have done in the analysis of beams, design of slabs, and design of footings. Just quickly refresh our memory. So what we did in beams, that we had a section. Moment. So we had a section. We knew what the reinforcement was, and then we found out what was MUR. Okay, this was in question. This is what we did in beams. In slabs, so we analyzed beams. We did not design beams. Okay, when we say analysis, we know the section and we find out how much it can take. In design, it's a reverse process. So we know the demand and then we design a section that can carry it. So we did the analysis of beams. We have not looked at the design of beams. Then we designed slabs. And in the design of slabs, the only thing that we knew was loading and the span. From that, we computed what was the demand. So this is what we knew. Okay. And then we found out what should be the depth of the slab and what should be the area of reinforcement. So these things were unknowns, and we found those out. How did we find the depth? Based on the deflection criteria. We found the depth, and then we have that, we looked at the large formula wherein if we know the depth and the moment, we can always find out area. What we are doing in footings is, again, we are designing footings. Here, we know what is the demand, that is, we know what is the actual load, and we know what is the safe bearing capacity of soil. From that, we calculated what is the plan area of the footing. So we have computed the plan area. The next thing that we have to calculate is what is the depth. The depth of slab was based on deflection criteria, but here deflection is not really a criteria per se. So the question is how to find out the value of D, or how to find out deflection. Now, if I go back, mhm, yeah. So if I go back to the formula of moment, yeah, here. So we know how to find out moment. We know how to, calculate the moment of resistance when I know width, when I know depth, and the depth of neutral axis and so on. But now here, what we know is we know what is the moment. We know FCK. We know width because we already found out the plan dimensions, and therefore we know what is the width. But we do not know what is XU. We do not know what is D. Okay. But what we do know is the maximum values of XU. What we do know is this, that the maximum moment that we can permit that section to resist is equal to mu max, which is this formula, 0.36 FCKB into XU max. We also know what is XU max for a certain grade of steel in terms of its total depth. So even just to quickly go back to that, we have seen it here that for Fe250 it is 0.53D, 415.48, 500.46. Oh, something wrong here. Yeah, 0.46 and 550.44. So basically everything except D is now known in the equation. The only thing that is unknown is D. Okay, so this was just for your information. Don't write it in the exam. Okay. So the grade of steel is Fe415. We know that for Fe415, XU max is equal to 0.48 times of T. Therefore, mu max is equal to 0.36 into FCK into B into XU max, and we have to multiply this entire thing by the lever arm, which is D minus 0.42 times XU max. Now what we have to do, we have to replace XU max everywhere with 0.48D. So this is equal to 0.36 into FCK into width into XU max times D is sorry. So this is 0.48 times D, and this whole thing times D minus 0.42 into 0.48 into D. That's all. So this is equal to 0.36 into FCK into whatever is the width, 0.48. We can bring D out from there, and it can be into D square, and then the only thing that is left is 1 minus 0.42 times 0.48. So 0.36 or uh, we can combine everything in one go. 0.36 into 1 minus 0.42 to 0.48, which is equal to this into 0.48. So it is equal to 0.138 into FCK into BD square. So now in this formula, we know everything except D. So just putting all the values, 1591.14 into, so we have to be consistent in units. This is a very common mistake. Since everything, so FCK is in Newton per mm square, which is megapascals. B is in mm, D is in mm. Therefore, this has to be in Newton mm. Therefore, 0.138 into FCK is 30 into width. Now, the dimensions that we have chosen is 3.5 meters. So if you look at this, the width of this section is 3.5 meters. You look at it in this section. So this is your bending moment, and the width is what it is in plane. So your width is 3.5 meters. So into 3500 into D square. Okay. Can someone please give me a value of D? Come on, anyone? Value of D?
A few seconds.
Yeah, okay.
0.3313.
Sorry?
0.3313.
It cannot be that small, right?
Root into 10 raised to 6, actually.
So 0.3313 into 10 power 6. It cannot be that big.
331.3
It's
after
Okay, so
multiplying
330.
it. Yeah,
Okay,
331.3.
yeah. So 331.36, we can write it as 331.4 mm. So this is the minimum depth that is to be provided. Now, just like we did in slab, we found out what was the span to depth ratio. We got the minimum value of D. Okay, there's no need for us to imagine that. We already have everything. Yeah. So we found out what is the minimum depth, 160 mm. Then we found out what is the capital D, and we just back calculated what is the actual effective depth that we have provided. So minimum depth is 331. We have to calculate what is the so minimum effective depth is 331. We have to calculate the minimum depth. So this is equal to d plus uh, bar bar diameter dia plus clear cover. Now you might wonder as to why I have taken bar dia and not bar diameter by 2 like I've taken in slabs. Here we said bar diameter by 2 because we designed a one-way slab, and in a one-way slab there's only reinforcement in one direction that is important to us. Therefore when we calculate d, it's half the rebar plus clear cover. But here we provide reinforcement in both the directions. So what we effectively have is, this is our section, this is our reinforcement in one direction, and this is our reinforcement in the other direction. And both of them are mean reinforcement. Is there's no difference here. So the average depth is at the, perhaps I'll use a small marker. So the average depth is at the center of both these. So this depth is the bar diameter, the entire bar diameter plus the clear cover. And therefore, here it is d plus bar diameter plus clear cover. Now the question is what bar diameter to use. Normally we've observed that for typical buildings 16 mm dia, 20 mm dia suffices. 20 gives us a better number, so let's assume 20. So 331.4 plus bar diameter 20 plus clear cover. Now I've said that the minimum clear that is to be used is 50 mm, but practically what we do is we at least provide 75 mm. So this is the minimum depth. So 331.4 plus 20 plus 75, it is 426.4 mm. Okay. So how much depth will you actually provide? Should I provide 400?
450.
Yes. So we have to approximate it. So we have to approximate it to 450 mm in multiples of 25. So it is approximately 450 mm. So this is our total depth. So now basically we are at a position wherein we know the moment, we know the depth. Now the only thing that we have to calculate is area. So basically this is what happens after the first step in slabs. So in the slabs, we use the deflection criteria to find out the depth, and perhaps this case does not apply here because we already know the loading. And then we just found out what is the reinforcement. So from here, everything is same. So the third step is the design of flexible reinforcement. So like I've said this before and I say it again, that normally the depth of reinforced concrete footings is governed by shear criteria. To, just to give you a sense of what I'm saying. So if the depth that you get from flexure criteria is 450 mm, perhaps you might get a depth of around 600, 650 mm from shear criteria. And that is the depth that we actually provide. But here, since we're not looking into shear, we are not, really bothered about what is the depth that we get from shear. But that, in most of the cases, is definitely more than 450 mm. So now we have to design a flexural reinforcement. We just calculate what is the actual effective cover. So this is equal to capital D minus bar dia minus clear cover. this is equal to 450 minus 20 minus clear cover is 75. So this is equal to 355 mm. This is our actual depth, actual effective depth. Now we have to use our so-called Thanos formula, this one. So AST is equal to 0.5 FCK by Fy BD into 1 minus square root of 1 minus 4.6 MU upon FCK BD squared. Might look scary at the first, but it's pretty straightforward. You can just save a lot of time if you learn this. So now all you have to do is plug in the values. So this is equal to 0.5 times FCK upon Fy into B. Our B is 3500 into D, which is 355. Okay. Into 1 minus square root of 1 minus, we have to be consistent with units. Our design moment is 1592, I believe, 1591.14. 15, perhaps I should write this again. 1594.1 into 10 power 6, so that it is in Newton mm, and we have to divide it by FCK BD square. FCK is 30, B is 3500, and D square is 355 square. Okay, now the task is quickly give me an answer for AST.
Bhargav, is
Yeah.
it 1591.14 MU?
Okay, I'll just check.
Yeah.
1591.14. So 1591.14. Yeah. Into 10 power 6. I thought you already had an answer and I was really surprised. 3500.
Is it 2786?
2786. Okay, perhaps this looks a little small to me. Anybody else? Come on, by this time you should be, really fast with these calculations. Come on, no one's got it?
2786.
What is it?
2786.4.
2786. Okay. Again, this looks small to me. Perhaps I'll just check my calculations again. 1 minus.
2694.5.
Okay, so another answer that we have is 2694. Okay, so the answer that I have got is 14,888 mm square.
Don't we need to multiply the mu term by 4.6? I think we haven't done that.
Oh, it is because of that you're getting a different answer. So you have to multiply this by 4.6. Can you just recheck? Getting this now?
Yes.
Okay. So this is our answer. So we have to provide 14,888 mm square of reinforcement along the entire width. That is what it means. Before uh, before we actually provide this, there's something that we should check. Now, if you remember, we talked about minimum reinforcement, and that the minimum reinforcement is 0.12% if it is 415/500, and it is 0.15% if it is Fe250. So the AST that the AST minimum that is to be provided is 0.12% of BD, of the gross area. So this is equal to 0.12 divided by 100 into can someone answer which is the gross area that we're talking about, or what is the gross area here? Or what is the area of the section here? Basically, what I'm asking is what is AG? So 0.12% of what is the minimum area? Okay, if you have understood anything about flexure, you should be able to answer this question. Now it's pretty simple that, you know, all the cards are on the table. We know all the dimensions. So the only thing that I'm asking is when I say gross area, which area am I talking about? Nobody? Okay, excellent.
That cross-sectional area, like
Yes, it's the
3.5
cross.
multiplied by the height, depth.
Yes, it is the cross section area. So this is our column. Okay, we are working in this plane. So basically this is nothing but a beam that if I, look in the section, if I look it in the section, so this is my beam, which has a width of 3500 and has a depth of 450. Okay, so this is my beam section. I'm going to provide reinforcement here. Okay, shouldn't have taken so long for you to answer this question. So this is my beam. Now it might look a little odd, but this is the width of that beam. This is in plan. This is the width of that beam. This is the span, and this is the depth. So when we say gross area, I look at the cross section of the beam, and this is the gross area. Okay, so 0.12 divided by 100 into 3500 into 450. An answer, please.
One 1.89 into 10 to power 5.
5,
Like
perhaps.
189,000.
10 raised to 3. 1.8 and 10 raised to 3.
Okay, so 1890 mm square. That is the area we have to provide. But what we are actually providing is 1,488, which is much more than the minimum area. Therefore, AST, which is provided, or what we have calculated, is greater than AST minimum. Therefore, we are okay. Or the design is okay. Therefore,
I had a question. In the paper, are we going to get this square footing only or rectangular also?
historically, you've been getting square footing. Basically, if I look at all the question papers before, it's all square column. It might be, you might be short of time in case you get a rectangular footing, but we have shortcuts for everything. So perhaps after we finish this, I'll give you a shortcut as to how you can take care of a rectangular footing. So now the only thing is you have to compute how many bars to provide, and how much spacing to provide, and so on. Just a moment. So if we provide 20 mm dia bars, the number of bars required is, of course, the total area divided by area of each bar. So this is equal to AST upon area of each bar. Our AST is 14888. So this is 14888, and the diameter of 20 mm diameter bar is pi by 420 square, which is approximately 314. So so the total number of bars turns out to be 47.4, which is approximately equal to 48. So we have to provide 48 number of bars here. Now, naturally, we should find out how much is the center to center spacing. So if this is my footing, I'm going to be placing the bars in both the directions. 48 bars in each direction. I just have to compute that what is the spacing of this. So so this dimension is clear cover plus phi by 2. This dimension is also the same. The dimension of the first bar from the edge. So this is clear cover plus phi by 2. Now I want to calculate what is the center to center spacing. Now this is the total width. So naturally I have to subtract these from this and then divide by the total number of bars. So the center to center spacing minus center to center spacing is equal to the total width. Perhaps I'll just denote this by width since we're using beef here. So you can denote it as L or small b, or whatever helps you understand. So this is the total width minus 2 times of this clear cover plus p by 2 divided by number of bars minus 1. Okay, because the bars are 48, the spacings are 47, and therefore b minus 2 times of center to center spacing, number of bars minus 1. So please just plug in the values. B is 3500 minus 2 times clear cover is 75 plus bar diameter by 2 is 10. Number of bars is 48. 48 minus 1 is 47. So the spacing is approximately equal to 70 mm.
70.85 after
Yes.
calculation.
Yes, correct. Very good. Fast calculation. So this is 70 mm. So that is the spacing that we have provided. Now the reason why we found this out is because of the clause that says that the maximum spacing should not be greater than 300 mm. So this is 300 mm, less than 300 mm, therefore we are okay. So this was just to check, nothing else. So if you are in a position that you don't have time, if you have short of time in the exam, you perhaps might just skip this step. Okay, I'm just saying, because this is not naturally, you're providing so much reinforcement. There are 48 bars, so you can just quickly divide 3500 divided by 47, and yeah, find 74 or something. So you are basically providing a spacing that is way less than 300. You get a feel of it, so you might just skip this step in case you are short of time. Okay, this is not a very important check. Of course, it is important, but with the numbers that we are dealing with, we can just get a feel that we are way within 300, and therefore this is fine. We are providing 20 mm diameter bars at 70 mm. That's pretty close. Okay, so we have everything we need now, but the only thing that needs to go on the site is not all these calculations, but an actual section. Therefore, we're going to draw an actual section. So first thing is that we have to show the footing in plan. So that's our 3500 by 3500 footing. Now we have to just don't draw these lines. I'm just drawing them for reference. So this is our 500 by 500 column. Okay. Now what we are going to do is draw a section here. Okay. So this is our section. Now we have to provide so don't waste your time by actually drawing 48 rebars. This is just a sketch to show to the invigilator that you have understood. Okay, so this is the rebar that you see in line is actually the rebar in this direction, like this, and the rebar that you see in circles is the rebar in this direction. Okay, so just a few more details to add here. First is, of course, how much reinforcement that you are providing. So we are providing 48 number, 25 mm diameter both ways. Then, of course, the most important thing is the total depth of the footing, which is 450. And then perhaps not very important, but still it's worthwhile to have it in the section that we are providing a clear cover of 75 mm everywhere. Okay. Now, in a good detailing, you will also see the rebar from column. So, just for the sake of it, show this rebar. So this is our final section. So any questions here?
I had earlier part.
Yeah, go on.
While calculating AST, my value came out to be 13,921, which you calculated as 14,888. So is
Okay.
that much deviation possible, or because I rounded out at some that square root wala thing, that value I rounded off to,
The best
I
thing to
guess,
do
point zero.
is use a calculator and do this entire thing in one shot. So you don't have to approximate at intermediate stages. So a normal mistake that I've seen students making is, uh, at least in the class, I don't know how they do it in the exam, but they go step by step like we did in school. So they calculate numerator first, then denominator, then square root, and then one minus that, and then the other thing, and then they multiply it. It's a royal waste of time. You just in a calculator you can do it in a single shot. I hope you guys know how to do it. You know how to use a calculator, right?
Not this kind of big thing like square root 1 minus this upon this. Whole shot. I have not
Okay.
explained.
So if you're using scientific calculators, uh, are, are you using scientific calculators? Okay. One step back.
Not
Do
right
you
now, but I
do you
have.
know? Do you guys know what a
Yeah.
scientific calculator is?
Yes.
Yeah,
Yeah.
you know it, right? So
Yeah.
if you happen to have them, there is a certain mode that you can set up, and using this mode, you can write this as you can see on the screen in your calculator, and as you do it, it'll not take more than a few seconds. So perhaps now I cannot. Uh, I'll just see if I can get a digital scientific calculator, and if I do, perhaps in the revision lecture, we can look at how to use a scientific calculator to solve equations like this without having to approximate it in intermediate steps. Okay, but
Okay.
to answer your question, uh, it should not really matter if we are doing it in steps or we are doing it in one shot. If you're approximating something, the value should be more or less within plus minus 2-3%. So in the wake of this question, is there anybody else who has got an answer as 14,888, or is it just me?
Yeah, I also got it.
Okay, then perhaps this is the right answer, and you just might want to recalculate this.
Okay.
So yeah, any more questions here? So now we have looked at beams, slabs, columns, footings. Anything else? So what is the takeaway from all this? In terms of solving your exam, what is the takeaway? So the nature of the question paper is like you first get a theoretical question, 10 marks or 15 marks, or is it 20 marks? I don't know. Yeah, I think it is 20 marks. So the 20 marks of theory, and then you get 4 questions out of which you have to solve 2. So naturally, one question is related to beams, the second one is related to columns, the third one is related to slabs, and the fourth one is related to footings. So out of those 4, you have to solve any 2. So what is the takeaway? We have talked about beams, columns, slabs, and footings. We've looked at all the numericals. Perhaps you really want to refresh your memory and go through all the numericals once again. But I would, what in terms of saving time and scoring better, what I would recommend is, come what may, do not miss the column question. It won't take more than 10 minutes tops, because the procedure is very straightforward. Uh, you see, the design of RCC columns. Just in 2 slides, we have sort of completed the design. It's very straightforward, and there's nothing challenging that you can face here. So come what may, do not you know leave this question. Solve this for sure. If you have to, among the other 3, beam, slabs, and footings, procedure wise, design of or analysis of beams is the shortest. Okay, perhaps I'll go at a numerical that we solved. Yes, so this is the beam numerical. 2 slides, it's done. So if I have to suggest an order in which you can look, or you can sharpen your skills to solve numericals, I would suggest go for columns first. Then you can look at design of beams. Okay, if you're pretty comfortable with both of them, then you can look into slabs, because design of slabs is also straightforward. You just have to find out what is the depth using this, and then nothing. 3 slides tops. So we have finished everything in 3 slides. So, and even after that, you feel the only problem with slabs is you're going to spend some time in detailing this. The sketch is going to take some time. But in beams, there's no sketch because you already know everything. The sketch is given. The data is given. There's nothing that you have to provide. Therefore, that's the simplest thing in beams. You don't have a sketch per se. You don't have to give a final drawing. In columns, you have to, but this is very simple, very straightforward. Shouldn't take much time. In slabs, you might have to spend some time in drawing the section. So, but considering the simplicity of the procedure in slabs, this would be third on my list, and then fourth would be footing. And the reason being, it's a little lengthy, and you have to uh, sort of understand the analysis first. When I say analysis, I mean you have to understand how to get the design moment. So this will be fourth on my list. Now there was a question as to what do we do if we get a rectangular footing. So perhaps I would answer this question. So if you get a rectangular column, say you get a column like this, so but you always have an option. You can provide a rectangular footing. Practically, a rectangular footing is provided when you have a rectangular column, but this is not uh, this is not a practical situation. You don't have to give an actual footing. So irrespective of the footing being rectangular or square, you can always provide a square footing. So irrespective of what is the area you can get, you can provide both sides. Technically, it is not going to be incorrect. The only thing is, see, basically we have to be right in terms of our understanding, and we have to be right in terms of theory. As of now, okay. So even if you get a rectangular column, you can provide a square footing. Now the only trick here is which section will you consider, or which moment will you consider. When I say that, what I mean is now you have two axes. So this is your x-axis and this is your y-axis. Okay. So now the column is rectangular, the footing is square. So which moment will you consider? Will you consider mx or will you consider my? Okay. Strictly speaking, we have to consider both moments. We have to provide both rebar accordingly. But in exam, we might not have time. Therefore, we have to choose one, and we have to provide the same in the other direction, which will be a slightly conservative, but it will be correct. Okay, you are not under designing anything. So my question is, which moment will you consider mx and my? When I ask this, what I really mean is, which moment do you think will be larger? Will it be mx or will it be my? Think about it for a moment and try to answer this question.
My.
My, okay. Uh, Anyone would like to add to that? See, these are very small things, and perhaps these are the things that uh, what I would say. These are the things that if if your understanding is on the right track, then these are the things that you easily understand. The procedure anyone can follow, not a problem. But now what we've learned is we spend some time on actually knowing how to calculate the moment. So we spend some time here. Hmm? So a simple question that I'm asking is, if the column is rectangular, the footing is square, then which moment will you consider? That will so naturally my question is, which of these moments is greater? So if you consider the greater moment, you'll provide greater rebar, and you can provide the same rebar in the perpendicular direction. You're covered. The footing is safe. You're not under designing it. So the question is, which of the moments is greater? Is it mx or is it my?
MX is greater.
Or along the y-axis, I guess, because
So okay. So to clarify what mx and my is, so this is mx. This is moment about x-axis, and this is my, moment about y-axis. Okay. So what do you think is greater, mx or my?
about y-axis, because The point is much farther than this.
Okay. So actually, the answer is opposite of what you just said. Uh, you see, we have two distances. Let's call this as L2 and let's call this as L1. Okay. So these are spans basically. When I'm finding mx, I will use the span as L2. When I'm finding my, I'll use the span as L1. Now it's it's obvious that L2 is greater than L1. Everybody agrees, or does it need a mathematical proof for this? It's simple, right? If this is the shorter side, it's a square column, it's a square footing. So naturally, L2 is going to be greater than L1. Okay. Q is
Okay.
same for
I was
both.
considering to be a rectangular footing, that's why. Okay.
No, no,
It
it's a
seemed
square
rectangular.
footing.
Okay,
Okay.
then about this.
Okay.
Then about x.
So, pardon the sketch. It might seem like rectangular, but I've said it multiple times as square footing. So if it's a square footing, L2 is greater than L1, Q is same. Now M, if you look at the value of M is Q into LL square. L is same because it's a square footing, Q is same because it's a square footing. The only thing is L1 and L2 are different. So naturally, whatever is greater, L2 is greater than L1, meaning that Mx is greater than My. So this is a larger span. So naturally, there is going to be a larger moment. And just correct the direction of moment. So if we are considering this, the moment is going to be like this. So this is Mx and this is My. So everything remains same. You start with finding out what are the planned dimensions. You provide a square footing. Then this, while calculating the moment, you just consider the longest span. So you consider L2, meaning that you consider Mx. You just find out what is the moment and everything remains same. So this is a shortcut. What you should actually do, or what you should, strictly speaking, what you should do is you calculate Mx, you calculate My, and provide ASTX and ASTY in the corresponding directions. Okay, does that answer your question?
Yes.
Okay, so perhaps I think we are done with all the numericals. This was it. So I really urge you to. It's just four types of problems, out of which three belong to flexure. So there's nothing new in this. The only the procedure to approach those problems is a little different, but fundamentally all the concepts remain the same. Only columns is a little different, but the upside is that it is the easiest of all. So, I really would urge you to look at all these numericals, not just before the exam, but definitely before the revision lecture, so that you have a good idea of what we are discussing, what you're talking about. So, if there are no questions here, uh, perhaps we can declare that the design of reinforced concrete footings is over, and we just have to jump to a few miscellaneous topics that are to be covered. So we'll just take a short break, perhaps a few minutes, and then we'll start with a new topic. It's not a topic actually. It's just a small part of the syllabus. This is grid flows. So it's 10:07 now. Let's start at 10:12 or so. Okay, but if by then there are any questions, I'm online. So again, the next topic of discussion is a part of something that we've already seen. We've looked at slabs and we've looked at the different types of slabs. Perhaps it is due to the speciality of these slabs or the rarity of these slabs, is that we are discussing it as a separate subtopics. So grid flows are nothing but flows resting on beams running in one or two directions. Talking about one direction, we have looked at what is called as grid slab, which perhaps is a type of a one-way slab in which the beams are running in only one direction, which are closely spaced as compared to when we compare it with a beam slab system. So we have a set of beams that runs only in one directions, and they are supported on either primary beams or columns in the other direction. Uh, in this system, the floor just has nominal thickness, while the grid of beams is the main supporting systems. And such a system is normally employed for architectural reasons, naturally, which are suitable for large rooms such as auditoriums, vestibules, theaters, showrooms, etc. Wherein providing a column-free space is the perhaps the main design criteria. Now you might have noticed that this is not a very common system, particularly because of the higher cost of the formwork and lower fire rating. The reason that this system has a lower fire rating is because all the elements are very slender, meaning that the slab is very thin, the beams are very thin, and therefore the fire rating is uh, not, perhaps it might not be adequate as to what is required. Generally, we follow a norm of at least 2 to 4 hours of fire rating. So you have to be careful about it. While perhaps not today, but when tomorrow you're doing actual projects and you're thinking of a waffle slab, you're thinking of a tire grid slab, you always have to keep this at the back of your head. Is it can satisfy the fire rating. It's always good to consult uh, with your uh, with your team who takes care of this, and just ensure that it has adequate fire rating. So looked at before, waffle slab. Waffle slab is nothing but an assembly of orthogonally intersecting beams placed at regular, and I would like to add close intervals, and interconnected to a slab of nominal thickness. So you perhaps you have this definition by heart as of now. Now, when we are placing the beams close to each other, what we are structurally doing is we are stiffening the system. We have looked at the example of how a plain steel, uh, I would say, plate has very less stiffness when you compare with a steel patra. So in a steel patra, what you're doing is you are corrugating it, or you are stiffening the system. Similarly, here, what you're doing is you're bringing smaller sections, smaller beam sections, which are very close to each other in both the directions. So you're really stiffening it. So basically, what it does is it makes the system lighter and stiffer as compared to a flat slab or a flat plate. Naturally, when you reduce the weight of the slab, if you have multiple slabs, so you can really have a lot of impact on structural design. As in, you can really reduce the weight of the vertical framing system. You can really reduce the design of the footings. So these slabs are particularly suitable for spaces which require seclusion from vibrations, like labs, hospitals, airports, and so on, and which are very sensitive to floor deflections as well. So two criteria: one is vibrations, another is reflections. Whenever these criteria are important, your go-to guy is waffle slab. In general, if we compare uh, for the same amount of span, if we compare the concrete quantity and the steel quantity, a waffle slab is has saves up to about 30% of concrete and 20% of steel as compared to a flat slab. Now, talking about the general thumb rules or dimensions that you can start a design of waffle slab, there is the overall depth can be somewhere in between 300 to 600. The slab thickness, which you can see it's very thin, is about 75 to 125 mm. The width of the beams is about 125 to 200 mm. Center to center spacing of beams can be between 600 mm to 1.5 meters, and the preferred spans is up to 16 meters. So anything between 10 to 16 meters, you can opt for this type of slab, and you can select your dimensions somewhere in this range, so that at least visually it looks correct. Of course, there's going to have to be a technical analysis and design as to what should be the exact dimensions. You're not expected to learn all this, but you should get a feel, and you should be able to provide elements that actually look at least structurally correct. Now, advantages include obviously it is they are more they're preferred when it comes to longer spans. They provide better structural stability because we are stiffening it. Naturally, if we are stiffening it, we are reducing deflections, we are reducing vibrations, and along with they, of course, they appear aesthetic. Then, of course, they are relatively light, therefore lesser foundation cost, lesser material in the vertical framing system, and therefore lesser cost of the vertical framing system. It requires less material, as you have seen. It requires about 30% less concrete and 20% less steel as compared to a flat slab. Then excellent vibration control, and perhaps it is economical. We can say that it is economical only when reusable formwork is used. If there's really complicated form of arrangement that you have that requires a custom formwork, then it is going to be really expensive. The downside is that it requires greater flow to flow height, because if you talk about flat plate, then you might require a depth of around say 300, max 350, but still you are not going as deep as 500, 600, and so on. So naturally this requires a greater flow to flow height. Everything comes at a cost. Then since the geometry is a little complex, and you have to be very precise while spacing these, they're already thin, so there is lesser margin for error. Say imagine you have a 100 thick slab or 75 thick slab, and the formwork is going up and down, so that's something you cannot afford. So there has to be skilled labor for this construction. Then it requires special or proprietary formwork, which is costly. Not every contractor has this formwork for waffle slab. So there has to be a specialized contractor, a specialized formwork consultant for this type of work. It is difficult to maintain. Naturally, there are so many surfaces, there are so many faces. It's flat slab, it's easier to clean, it's easier to maintain. But when it comes to this, if it is not maintained properly, you might just lose the entire reason for which you build that type of slab for aesthetics. And if it is not maintained properly, there are going to be webs, and there's going to be a lot of dust because the number of surfaces are more. Therefore, it is very difficult to maintain. We talked about this low fire rating due to thin members. Fire rating is a function of the thickness of the member. The thicker the member, the better is its fire rating, because you provide there's more amount of concrete. There's a better cover to the reinforcement, and therefore there's a better fire rating. Here the members are thin, the reinforcement has very small cover, and therefore the fire rating is also small. Now, there's always a question of services when it comes to waffle slabs. Where do pass the services? It is below this. Is it below the beams? It is through the beams, and so on. There are a lot of options. But if it is passed through the beams, then again, the entire point of providing waffle slab, which is an important reason for providing waffle slabs, which is aesthetics, is again gone, and that degrades the appearance of the exposed waffle slab. So, always keep services in mind. Always, have a discussion tomorrow when you're doing an actual project. Always, coordinate this with the MEP consultants at a very early stage as to, if I'm providing waffle slab, how are the services going to go? Because you really don't want to see all those holes in your beams at regular intervals. So, just make sure that you take care of this when you do an actual project. Now, another type of diagrid slab, perhaps less commonly used and used only when there are really complex geometries, is what is called as diagrid slab. This is nothing but a portmanteau of diagonal grid. So in this, the beams, the beams are not along the span. So the beams are perhaps at an angle to the slab, and so it is nothing but a framework of diagonally intersecting concrete beams that is used in the construction of buildings and roofs. And this is only preferred in case of complex geometries and curved supports. So waffle slab itself is a little complex, and you really don't want to further provide a diagonal grid and then make it more complex. So, but if your support is say not orthogonal, it's not a regular grid of columns in both the directions. So if it's a curved support or complex geometries, it is only in that case you can look at the use of diagrid slabs. Otherwise, provision of waffle slab is more than enough. So I believe this is all that we needed to know about what are grid slabs. So if you have any questions, we can discuss them. Else we can jump on to the next topic.
I had a question.
Yeah.
So it's related to the IDS project that my span is slightly greater than 16 meters. It's about 17.5. So in that case, do we increase the depth of the waffle? Because I have taken it approximately 700. So
that should
does
suffice.
that
I
work?
think that should suffice. So
Okay.
so 16. So So 16, what the slide says, these are just guidelines. It's okay if you're a little here and there. This is just to give you a range in which you can operate a waffle slab. It's okay if it's 17.5, 18. Okay, it is not the end of the world. This is not the Lakshman Rekha. That is, if you cross it, you're just gone. So these are just guidelines. You can always go 5-10% here and there. That's fine. The reason for giving a limit is it's not that you have a span of 24 meters and still you're constructing waffle slabs. So just it's fine if it's a little more or less. That works. Okay.
Okay. And another thing, regarding how do we support the waffle? Like, it's just a not a drop panel, but yeah, maybe the thing you see in this image, is that enough, or do we also have to give beam strips in between?
No,
Is
this
that
is enough.
necessary?
This is more than enough. The
Okay.
entire point of providing is a waffle slab to get rid of bigger beams. So
Okay.
you just have to have adequate shear strength at the support, and for that, if you have a plain section around the column and then a waffle slab all around, I think that should suffice.
Okay. All right. Thank you.
Yeah. Okay. If there are no more questions, we'll jump to our next topic, which is steel concrete composite construction. Now, this is one of the projects that we did a few years back, and we had a site visit a couple of years ago. And I would like to say that this was one of the cleanest sites that I've ever seen. And naturally, the reason was it was a composite structure, very clean, very, it was, the spans were adequate. And we, okay, the point is that it was one of the cleanest sites because the construction was composite. You could see, the sections were small, and aesthetically it looked really good. Not only from the image that I've shown, but if you actually go into the structure, even there, none of the components of the structure look really bulky or look really ugly. And I believe the reason was because it was a composite construction. Therefore, the columns could be smaller. The slab thickness was smaller, and everything looked pretty good. So a composite structural member is made up of two or more different materials. Fundamentally, what we do is we just take properties of each material and combine them to form a single unit that has an overall better performance than its separate constituent parts. Now, in construction, there are a number of composites that you can use. There's steel timber, timber concrete, plastic concrete, and so on. But the most common is steel concrete. And basically, when we are studying reinforced concrete itself is a composite material. But when we specifically say that we are looking at steel concrete composite, we are not using steel in the form of reinforcement, but so let me reiterate this. We are not using steel only as reinforcement, but also we are using structural steel sections. Perhaps I would just give, yeah. So this image first, so that you understand the difference between reinforced concrete. So reinforced concrete is a composite material, but you're using steel only to reinforce it. Okay, but in steel concrete composite, you're using steel not only as a reinforcement but also as structural members. So that's the difference between reinforced concrete and composite steel concrete. So the working principle remains the same. The working principle that we have seen in reinforced concrete. Concrete is really good in compression, very weak in tension. Steel, on the other hand, is very strong in tension, and it can resist a significant amount of tensile forces even in small areas. And steel is also good in compression. So when we combine, the powers of the two, what we get, the end result is a highly efficient and lightweight unit that is not only strong in compression but also in tension. So the working principle is the same. Now, this system perhaps has worldwide acceptance as an alternative to steel concrete. It offers common solutions that are economically competitive. Now, in almost all the retrofit projects, wherein a structure is already being built and there are changes that the client wants, there are some changes that the architect wants. Almost everywhere we go for a composite system. Maybe deleting some slab, adding some slab, or adding some beams, adding an extension to the existing structure. So whatever retrofitting activities, we perhaps look at composite as the first solution. So the primary components of steel concrete composite are obviously composite slabs, composite beams, and composite columns. Have we looked at a composite foundation, anyone? So when we studied foundation, I'm not talking about this semester only. So when you study foundation anytime, do you remember if we looked at composite foundations?
Would grillage foundation count?
Yes, yes, very good answer. So grillage foundation, we looked at that, wherein there's a set of steel beams orthogonal to each other in different layers, and everything is covered in concrete. That is a form of a composite foundation, but it is very, very, very rare, and therefore I'm not included here. And we've already looked at it. So this is how a composite slab looks like. So there's a steel decking. It might have a shape of a it might resemble the shape of a trapezium, well, trapezium decking, trapezoidal decking, or it might have a shape of a reentrant. So we look at it later. That is called as reentrant decking. The concept being that there's this steel decking and there's this nominal reinforcement that you provide in both the directions, and the concrete sort of sits on it. So that's a simple, way to explain composite slabs. So typically constructed as reinforced concrete slab cast over profiled steel decking, and the overall depth is at least 130 mm. Now the steel decking has sort of dual role here. First is that it acts as a formwork and a working platform during construction. So when we are dealing with the composite slabs, the steel decking itself acts as a formwork. Perhaps that is the reason why that the site looked so clean, because there almost no way there was a lot of formwork. And during the actual functional stage, it acts as an external reinforcement. So the reinforcement is not in the form of bars, but it is a form of steel decking. So the concrete and steel, of course, we'll see how they are connected to each other and how does a force transfer occurs. But during the functional stage, it acts as an external reinforcement. Reinforced concrete, on the other hand, so the question is, can you use only a steel profile decking? The answer is no, because naturally it's not going to be as stiff as concrete, and therefore it might undergo a lot of reflections. You can just imagine it. There's only a profile decking. There's no concrete. You just kind of get a feel that it is going to deflect a lot, and it is not going to be resistant to vibrations. Of course, the vibrations are going to be all over the place, and there's going to be no fiber or thermal protection at all. So that is the reason we provide concrete over the steel decking, because it stiffens. When it stiffens, it naturally reduces the deflections. It naturally reduces the vibrations, and concrete naturally has a better protection to fire and thermal insulation. So this is how a typical layout for composite slab looks like. So you can see a grid of columns. So the beams that are connecting to the column in y directions are your primary beams, and the beams that are connecting to either the columns or the primary beams are your secondary beams. And your composite slab sort of sits on the secondary beams in this direction. So your profile will be in this direction and there'll be concrete over it. The thumb rule that we follow is that we do not go for a span which is more than 3 meters, at least for a. So what I mean by that is the secondary beam should not be located at a distance of greater than 3 meters. Recently, we did a youth study when we were studying the possibility of composite system for a mall that was planned to be built in Mumbai, and that there was we extensively studied the system, and the thumb rule that we followed is there has to be a primary beam along the shorter direction. So you also have you can also do it other way. Okay, I'll just tell you what I mean by this. So this is one way of doing it. The other way of doing it is that you have columns here, and you provide primary beams like this. Okay, and you provide secondary beams like this. Perhaps I'll use a different color, and you use secondary beams like this. Okay, perhaps I'll use a rectangle for column. So, do you notice the difference between these two systems? So what we've done here is we've provided primary beams along the longer span. The load remains the same, but we have provided primary beams along the longer span. What happens in that case is you get a larger section for a primary beam, and the secondary beam section might remain the same. But definitely, if you're going for a this type of system, if your primary beam is along the longer span, you're going to get a greater dimension. So the thumb rule being all your primary beam should be along the shorter span. So this is a 7 meters by 7.5 meters by 6 meter span. So your primary beams are going to be along the shorter span, and then the secondary beams are going to be along the longer span. This is a typical framing of composite slab. So yes, there are two deckings that are commonly used: a re-entrant decking or a trapezoidal decking. When I say depth of these deckings, it is the distance between the trough and the crest and the trough. So that's what is the depth. So a depth of normally 50 to 60 mm is sufficient for spans up to 3 meters. And this is what we normally use. I've told you before that we sort of restrict ourselves to a span of 3 meters. But in extraordinary cases, the span is say 4 meters or more, we can go for a depth of 80 meters. And in very rare situations wherein you want to span 6 meters and above, you have to go for a deep decking, which is about 200 mm. So now you can see that this is the depth of the decking only. Then you will have concrete above it. So 75 mm concrete and so on. So basically you're losing uh, the purpose of providing this. You can go really shallow with a steel deck. And now for 6 meters and above, you require 275, 300. You can work with a flat slab. There's no need to go for a composite slab. So, it's uh, just this. The first one is, I think it's okay for design. If you're actually framing, if you're actually working on the framing of composite slabs, perhaps, this is the depth and this is the span that you can work with. Now, just a few salient points about the profile decking. You may see that there are these corrugations uh, very closely located to each other, and these are nothing but they serve as a key for the concrete to interlock. So the concrete interlocks with the steel decking with the help of these corrugations or with the help of these keys. Now you might notice that there's also a reentrant corner at the top. Now, if it's a plain section here, what might happen is it might undergo local buckling because it also has some span. There's concrete on the top of it. There's going to be a dead load, live load, superimposed dead load, and so on. So there's a chance that this might actually locally buckle. To avoid that, what is being given is a reentrant stiffener. So this stiffens the section and reduces the deflections. Then another, and I think a very important section is a composite column. So you can do it two ways. You can either put concrete inside steel, or you can put steel inside concrete. Okay. So when you put steel inside concrete, the resulting section is called as concrete encased steel section. And when you fill concrete inside hollow steel sections, it is called as concrete filled hollow steel sections. Uh, uh, I don't remember the abbreviation that we commonly use. CFTs, concrete filled tubes. That's the abbreviation that we use. So perhaps this is the best use of this is an ideal way of combining concrete, reinforcing steel, and structural steel, because concrete the concrete is basically used for. Okay, let me put it this way. So concrete is very strong in compression. You can expect high compressive stresses in columns, and therefore it is the best use of concrete. Steel, it doesn't matter tension or compression. It has equal strength. So an ideal way of combining all the powers or all the qualities of concrete, steel, and structural steel is use it in the form of composite columns. You will see that such a type of system is more preferred in commercial establishments. It may be malls, or it may be so wherever you require maximum usable floor space, because especially in commercial establishment, the cost per square feet is very high. So if you can really work on reducing the size of the column, then you basically are making a lot of money for the client. So naturally, they're preferred in commercial establishments like offices, shops, malls, and so on. Now, as I mentioned before, there are two types. you see the first three fall under the category of concrete encased section. So there is a steel section within concrete. So in type 2, perhaps the two faces are exposed. In type 1, none of the sections are exposed, and in 4th, all the faces are exposed. The other way of doing it is there's a hollow tube, it may be rectangular, square, and so on, and concrete is filled inside it with a nominal amount of reinforcement. And the third way, in which we can combine both, is that there's a steel tube at the outer face, then there's concrete, and there's an I section within that. So this is sort of a combination of both of them. So this is concrete filled circular section with additional I section. Perhaps a very tight situation, this might be used. Uh, so the advantage that the first type gives is that concrete protects steel from naturally from corrosion and fire. And the advantage that we have in a second type of system is that the concrete is encased in the steel tube, and therefore it sort of prevents the steel tube from locally buckling. So we have seen that in corporation members, buckling is a very important design criteria: local buckling, global buckling, and so on. So if you have something to stiffen it from inside, it reduces the it prevents the section from buckling locally. So I believe we'll just stop here for now. The only thing that is pending in this topic is composite beams. We'll look at it in the next lecture, and a few other topics. Uh, Perhaps I'll just give you a summary of what is remaining. Yeah. So we have spent a lot of time on number 2. Then we have finished topic number 3 also, rectangular decorated die-grid. We have finished the theory of flat slabs with column capital, drop panel, flat plate, and so on. A few topics that are left is precast concrete elements, its applications and suitability. So we'll spend some time on this in the next lecture, and perhaps wind up topics number 2, 3, and 4. Neeraj has covered topic number 1, and if you have any questions regarding it, perhaps next lecture is the last time you can ask it. So it also depends upon how much time do we have. So if there's any specific topic that you want me to explain from section 1, you just let me know in advance. We'll take a look at it. So 2 lectures to go. I think the next lecture should be sufficient to wind up whatever is left, and we'll reserve the final lecture for revision. So if there are no questions, then I think we are good to go for today. I just record attendance. Yeah. So any questions in what we've learned today?
Yeah, I just have a small question.
Yeah, go on.
In the six types of sections that you showed us, the concrete and steel combinations.
Yes.
Yeah. So for the fourth one, is it the difference between this and normal RCC? Is it the member sizes of steel? Because
Okay.
RCC also has this, right?
Yes, but RCC does not have this steel section on the outer side.
Okay, all right. Yeah.
So yeah, perhaps that I should have pointed that out.
Huh.
That the dark line that you see is actually a steel section. This is a hollow rectangular tube. This is a hollow circular tube.
All right.
Perhaps
Thank
this will
you.
give. So this is what the section is.
Okay. Yeah.
Okay.
All right. Thank you.
Yep.
Hello.
Yeah.
How much does it exceed the cost, like overall, in the composite tech, like using the composite materials?
So it is not a straightforward question to answer, because it is always going to be dependent on a number of factors. Firstly, how much is the scale of the project? So how much? So what we follow is we sort of first develop a framing for both systems, because the spans the spans and the size of sections might be different in both the systems. So, and the next step is how much space are we really saving? And the third step is what is the cost of the space that we have saved? And the fourth step is what is the total cost of the construction of one type of system and the other type of system. Now, if I have to give an example, so we studied three systems for a recent project. So we studied an entire steel system, we studied a steel composite system, and we studied a concrete system. Now, in terms of space, yes, we were saving a lot of space when we were using a composite system, but in terms of cost, the reinforced concrete system proved to be the cheapest one. And it is always you always try to balance to you always try to strike a balance between the cost of the space and the cost of the construction. So the client went ahead with the reinforced concrete even though the sections were larger. So it depends on number of factors and never state there's an extensive study that has to be undertaken to understand which system is really most efficient in terms of cost.
Okay. Yeah.
Okay, any more questions? Okay, so thank you for today. We'll meet on next Saturday same time. Thank you.
Hello.
Yeah.
Hi, Bhargav. I had a question regarding the